say we have this base 10 number, for example 13, and we wanted to find the binary representation. Typically what we were taught to do is just to divide by 2 and find the remainder. For example, first step, divide by 2, the remainder is 1. This will be the first least significant bit, and so on and so forth. So that works and all, but I just kind of wanted to show why exactly this works, and we can uncover that by looking at the actual binary representation. So we have 13. Let's just assume we already know the binary representation. Of course, that's going to be 1, 1, 0, 1. And when we format that into a base 10 format, of course we get 1 times 2 to the third, 1 times 2 to the second, so on and so forth. So now we have this equivalency. So this base 10 13 is equal to this, which represents the base 2 representation. Of course, when we're solving this, normally we obviously don't know the binary representation, but let's just assume we know it for now, because this will uncover how this algorithm actually works. Okay, and now what we have to do, following the algorithm, we have to divide everything by 2. So divide by 2. On the left side, it's pretty easy. All you got to do is just subtract 1 from each of these exponents, like so. We draw that smaller. And then when we get to here, we get 1 times 2 to the negative 1, which we could just write to make it simpler as 1/2. Right? So we have all this. Now, when we take the right side, dividing it by 2, we get 6.5. Now, when we are doing this algorithm, what we're doing is we're finding the least significant bit to the most significant bit. So for our first division, we're finding the least significant bit, right? Because say we're just doing like the algorithm 6, 3, yada, 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 and we get 1, 1, or we get 1, 0, 1, 1. We're reading the bits from this being the most significant bit all the way up to this being the least significant bit. So for our first division, we're finding, like I said, the least significant bit, which in this case would be this position, and obviously in the binary would be this position, right? So we're finding that. Let's go ahead and simplify this side real quick, just to bring everything together. So we got 1 times 4 plus 2 plus 0. 4 plus 2 plus 0 will equal 6, plus 1/2 equals 6.5. Now let's consider for a second, instead of a 1 here, what if we put a 0? Obviously this is the wrong bit representation, but we want to show how dividing by 2 can uncover why that bit position is wrong. So if we have that, then this will equate to 0, and then this will equate to 0, and this is not an equivalency because we have 6 equals 6.5, right? So essentially what this uncovered was that whenever we divide by 2, we're showing that if there's a remainder remaining here, that means that when we have a remainder remaining, so this 0.5 in 13 divided by 2, that represents that the next least significant bit has to have a 1. Because whenever we divide everything by 2, in order to encapsulate that, this least significant bit that we see here has to equate to a 0.5 in order for us to keep the equivalency. So that follows when we do in the regular algorithm, we do 13, 6, the remainder 1. We're uncovering that there has to be a 1 in this least significant bit here in order to maintain that equivalency. Right. Let's continue this train of thinking for the next step. Okay, so we're going to divide by 2 again. 1 times 2 to the 1 plus 1 times 2 to the 0 plus 0 times 2 to the negative 1 plus, so we're just going to divide this by 2. We have 0.25 equals 3.25, right? Now, let's go ahead and quickly determine this side to be 3 plus 0 times 2 to the negative 1 plus 0.25 equals 3.25. Now, when we're doing this, we didn't actually have to bring this 0.5 down, because just with basic arithmetic, what we can do is we can just subtract both sides by 0.5, right? And now we don't even have to worry about these decimals at all, right? Now we just have this. And I'm just going to go ahead and bring it back. And for the case that, say we had a number where there wasn't actually a 1 for this least significant bit, then that means that we wouldn't have a decimal here at all, right? So basically what I'm trying to say is, for every step, we can find a way to just get rid of the decimal. So that way we're kind of resetting back to an instance where we just have the integer like we originally had. So let's just do that again. Let's just delete all this. Okay. And then we have a 3. Now, because this division here resulted in a whole integer, this next least significant bit has to be a 0. Because if it was a 1, if this was a 1, this would end up as 3.5, and this would not hold equivalency with this whole number, this whole integer, 3, right? So again, we're just kind of recursively uncovering in this kind of like base 10-bit expression whether for the next least significant bit, so for example, the first step, this was the least significant bit, and then now this is the next least significant bit that we're trying to uncover, whether that spot, in order to maintain equivalency, has to hold a 1 or a 0. And following this same kind of algorithm, we can kind of continue on for the whole thing until we can kind of recreate this kind of formula and find the original bit string, which is basically how this kind of dividing by 2 and remainder algorithm works. It's kind of just a shorthand for doing this. So anyway, that's the arithmetic interpretation of why that works. I also wanted to cover how this works. So when you're doing floating point representations, in order to find the bit representation for the decimal side of the floating point representation, for example, if we had, let's say we had some decimal 0.59375, this would be 10011, in that this would be 1 times 0.5 plus 0 times 0.25 plus 0 times 0.125 plus 1 times 0.0625 plus 1 times 0.03125, right? So when we're solving this, we have another shorthand type of algorithm where what we do is we take the original, multiply it by 2, and then we get 1.1875, and then we say, oh, if there's this kind of whole number to the left of the decimal point, that's a 1, and then we just kind of keep going until we end up creating this 10011, right? And it's inverse to how we did it before. So how we did it before was our first division gave us the first least significant bit. Here we're going to be going left to right. So when we find this bit to be 1, it's going to be the leftmost bit, and then this one, and then this one, and this one, and then so on and so forth. So that's the algorithm for that, but we're also going to examine why this also works. So let's go ahead and I'm just going to go ahead and shrink this down some so we have some room. Okay, so this is the binary representation for 0.59375. Now, let's see what we did for the algorithm. We multiplied everything by 2. Okay, so multiplying this by 2, we get 1 plus 0 times 0.5 plus 0 times 0.25 plus 1 times 0.125 plus 1 times 0.0625, and that would equal our 1.1875. And can you notice the pattern here? So basically, what we did is that for each one of these bits, we just kind of like jumped it over to the other side, right? For example, you see how originally we had 0 times 0.25. We just kind of jump it over here to be 0 times 0.5. Better example would be here, where we jumped it here. Originally we had 1 times 0.0625, jump it over, now we have 1 times 0.125. And that's just how the nature of multiplying by 2 works. And with that, we can say we have this kind of, this magical spot over here, right? When we multiply 0.5 times 2, we get 1. Okay, so this is kind of like the magic whole number spot. When this 1 bit jumps over to this magical whole number spot, we get a 1, we get a whole number. So basically, since everything to the right cannot surpass 1, cannot be an actual whole number, the only time we have a number greater than 1, or a number with, say, like a 1 to the left of the decimal point, is if one of the bits jumped into this whole number position to bring the value to above 1. So as you can see here, since our multiplication resulted in a value greater than 1, we have this bit here, which equals 1, indicating that our first most significant bit, which was what we found to be 1 times 0.5, has to be a 1. Because if it wasn't a 1, this would be 0. And then we'd have some value less than 0 equals some value greater than 0, which obviously does not work. So yeah, we just found the first most significant bit. Let's just write it here, right? we just uncovered the first most significant bit. So we basically uncovered that this is supposed to be a 1, it can't be a 0. And then, like before, we can kind of reset the problem by subtracting both sides by 1. And then now we have 0 times 0.5, yada, 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 equals some decimal value less than 1 because we subtracted 1. And yeah, all we got to do is just kind of rinse and repeat that until, so basically in this case, if we multiplied this side by 2, it'd be some like 0.37 or whatever. And since this bit jumps to the whole number position but it's a 0, this indicates that both sides are less than 1, are both decimal values. Thus, this next most significant bit has to be a 0. If it was a 1, we'd have a value greater than 1 equals a value less than 1, which obviously does not work. And with that, if we just keep following the algorithm, we'll end up with 1 0 1 1, 1 0 0 1 1. Sorry. And essentially, that's how that algorithm works arithmetically.